Well, hello there. This might be the moment that your appreciation of math changes. So get ready. We're going to talk all about the binomial theorem. And actually, we're leading up to what's formerly the binomial theorem. We'll talk about it in class, but I'm going to kind of give you some examples that give you an idea of the power of this thing called Pascal's triangle, and then how it can help us to expand our binomials. So let's take a look. We've got 5 examples here. 2 of them are at the level 2 idea here. So we've got some examples which will show us how to expand, but we need a little introduction first. It's an introduction to what we call Pascal's triangle. And it works a little something like this. It seems like kind of like a frivolous thing, like, oh, there's this triangle and it's got all these numbers, but you'll see that it's going to be really cool and powerful and has all these patterns in it. So the way this works is we're going to start in row 0 with the number 1. Easy enough. Along the sides of this triangle we're going to create, we're going to put 1s along the sides. So we'll start in row number 1, right, with a 1 and a 1 to the left and to the right of the original 1 in row 0. So we start at row 0. There's a reason for that I'll get to in just a little bit. All right, after that, we're going to put 1s along the sides of the triangle. And then every number in the middle is going to be the sum of the 2 numbers above it to the left and to the right. Right, so this little gap right here, we're going to fill with 1 plus 1 because those are the 2 numbers above 2. All right, so we get 1, 2, 1 in row 2. In row 3, we're going to put 1s on the sides. All right, and then we are going to put 1 plus 2 right below those 2 numbers, which is 3. And then 2 plus 1 right below those 2 numbers, which is also 3. And when we continue to expand, we're going to have 1s on the sides, and then the sums of the numbers above that number right below. So here on the next row, row 4, right, we've got a 1, a 4, because 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then a 1 on the side. What do you think row 5 starts out with? I wonder. 1, 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and 1 on the end. So here we go. 1, 5, 10, 10, 5, 1. All right, and this triangle continues on indefinitely because we can always continue to add more rows, right? And we get all these values, and I'll show you that in a second. Where does this come into play? Well, the row that we're on is going to give us an idea of the coefficients when we expand to that power. So for example, x plus y to the 5th, when you work all this out, like you could go through, you could do the box method, you could, just FOIL, you could do all kinds of stuff. And when you work out x plus y to the 5th, all right, it ends up being 1x to the 5th plus 5x to the 4th y to the 1st plus 10x cubed y squared plus 10x squared y cubed plus 5x to the 1st y to the 4th plus 1y to the 5th. And I highlighted here in bold these numbers that are the coefficients for the expansion here. And where do we see those numbers? Well, they're in the 5th row of Pascal's triangle. All right, so this magical triangle right here is going to be a quick way for us to actually expand without having to do extensive amounts of FOIL. By the way, just in case you're curious, people are like obsessed with this triangle, or okay, they write it out in all kinds of rows. So somebody on Wikipedia, this is open to everybody, all right, wrote out the first 30 rows of Pascal's triangle. You know, all it goes down to row 0 all the way to where we have 29 right here, and then look at all these big numbers right here. And so if we were to do an x plus y to the 29th, these would be all the coefficients on that expansion. Oh, try this out. Use Pascal's triangle to expand this binomial 2x plus 3 to the 4th. So the first thing is use a pattern of increasing and decreasing exponents to write your terms without the coefficients. What does that mean? Well, take your power, which is to the 4th, and raise the first term to that power. So I would write this as 2x to the 4th, and then the 3 gets whatever's left, okay? So whatever's left is 0 because we've already used up our 4 powers basically on the 2x to the 4th. And I'm leaving a little blank right here because the coefficients will go right there in just a second. All right, then we go down a power with the 2x. So we have a 2x cubed. That'll raise the 3 to the first power. So notice that 3 plus 1 gives us a total power of 4. So everywhere around here, we should have a total number of exponents as 4 here. Then we go down a power with the 2x and up a power with the 3. So 2x squared times 3 squared. Down a power with the x, 2x to the first times 3 cubed. And then 2x to the 0, which is just 1, and then times 3 to the 4th. And then the magical part about this is we can use our coefficients from Pascal's triangle to fill in the blanks. So if we scoot on back, we notice that on row 4, our set of coefficients, hopefully you've written this down because it's on the notes, all right, but we got 1, 4, 6, 4, 1. And those coefficients fit in really nicely in each of these blanks, 1, 4, 6, 4, 1. And then, of course, we can clean it up, all right, by simplifying. So we get a 16x to the 4th plus a 96x cubed. This is a 2 cubed times 3 times 4 gives us 96. A 216x squared and a 216x plus 81. All right, so these coefficients made it really quick to expand something that would take forever to do, it seems, if you were to just FOIL this out. All right, so use Pascal's triangle to expand this binomial x minus 2y to the 5th. All right, use this pattern of the increasing and decreasing exponents to write our terms without coefficients. So we're going to start at an x to the 5th. That's our first term. And then our other term is negative 2y, which will raise to the 0. So 5 plus 0 gives us a power of 5. Go down 1 with the x. So we have an x to the 4th times negative 2y to the 1st. Down 1 with x, up 1 with the other term, negative 2y. Down 1 with x, we get x cubed times negative 2y squared. X squared times negative 2y cubed. X to the 1st times negative 2y to the 4th. X to the 0 times negative 2y to the 5th. All right, so we're just writing all the possibilities, basically, of powers of x and powers of negative 2y. But they have to add up to 5. So now we need to fill in the blanks with coefficients from Pascal's triangle. If you look on the 5th row, those coefficients are 1, 5, 10, 10, 5, 1. All right, you'll use a lot of these so often that hopefully it'll just like kind of be right there for you. All right, and then we can simplify by multiplying out. We get x to the 5th minus 10x to the 4th y plus 40x cubed y squared minus 80x squared y cubed plus 80x y to the 4th minus 32y to the 5th. Notice we're alternating signs here, and the reason why we're alternating signs is because this negative 2y is raised to an odd power sometimes and an even power other times. All right, so the binomial coefficient in the expansion of a plus b to the n, all right, this coefficient, we can get it through Pascal's triangle, but there's also another formula, which we call a combination, NCR. I'll show you a button on the calculator down the road, all right, but basically it is n factorial over n minus r factorial times r factorial. And it's going to show us all the different ways that we can rearrange r things among n total things. Now, you don't need to know that when we get to stats. If you get to stats, then we're going to talk about that in more depth. But for right now, all you need to know is how to calculate this. And a little reminder, this n with an exclamation point we call factorial. I kind of skipped right over that, but it's basically the product of all the positive integers up until n. So for example, 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And this is just a shorthand for writing the product of all those numbers. So, for example, we don't have to necessarily rely on Pascal's triangle to find this coefficient, right? Although it's quick. If we wanted to find something like the coefficient of the third term of the expansion of x minus y to the 10th, we would have to get all the way to the 10th row of Pascal's triangle. It's not hard, but you got to write a lot. You got to find out a lot of stuff. But this formula is actually an even faster way of doing this. So by the way, notice that the third term is the x to the 8th times y squared term if we think about our expansion. So remember the way we wrote it. The first term would be x to the 10th times y to the 0. Second term, x to the 9th times y to the 1st. Third term, we're going down by 1 with the x power and up by 1 with the y, and that's the x to the 8th y squared. So what we need to do is find out what 10 choose 2 is. That's how we pronounce this coefficient right here, right? Because we want the second term with the y, so that's where the 2 comes from. So we would say 10 factorial over 10 minus 2 factorial times 2 factorial, which is 10 factorial times over 8 factorial times 2 factorial. And if we were to write all of this out, 10 factorial is the product of all the numbers up till 10. 8 factorial is the product of all the numbers up to 8. And then we've got a 2 and a 1, because that's 2 factorial, 2 times 1. But you notice that a lot of these numbers cancel out, right? There's a lot of 8 factorial that's contained within 10 factorial. And in fact, everything all the way up until 8 cancels out. So we're left with a 10 times 9 divided by a 2 times 1, which is 45. So thus the term is 45x to the 8th times negative y squared, and the coefficient is 45. In summary, Pascal's triangle, it's so useful and it's so nice. There's so many patterns that we didn't even get to discover in this video. We'll talk about binomial expansion, all right, and how to quickly find an expansion rather than relying on FOIL or all those other techniques. And then later on, we'll talk about how this connects to probability. Thanks for watching. We'll see you on the next video.